We will now apply the first law of thermodynamics, the first law in short, to the cases of pure substances under conditions where these pure substances do not undergo a chemical reaction or a phase change. First, let's assume that the pure substances are in an isolated system. By definition, such systems cannot exchange work or heat with the surroundings. So their energy cannot change, and we would write W equals 0, Q equals 0, therefore delta U equals 0. Next, we consider the isothermal expansion or compression of an ideal gas. Because we are considering an ideal gas, we are considering a substance where there are no interactions, a substance where the energy is only present as kinetic energy. So when we expand or compress this substance, we change the intermolecular distances, but this will not change their intermolecular energy, since this is neglected. The isothermal conditions ensure that the kinetic energy of the particles does not change. Hence, the total energy of the molecules making up the ideal gas remains constant. The change in energy of the system is therefore equal to 0. So we conclude from the first law that for the isothermal expansion or compression of an ideal gas, the heat exchange between system and surroundings is the opposite of the work, or Q equals minus W. We learned in the previous lesson how to calculate the work of expansion or compression of an ideal gas under isothermal conditions. Now, using the first law, we know how to calculate the corresponding heat. For the adiabatic compression or expansion of any substance, we can write Q equals 0. Hence, from the first law, we conclude that the work of expansion or compression is equal to the change in energy of the substance. Next, we consider the isochoric heating or cooling of any substance, gas, liquid, or solid. Isochoric means that the volume is constant. In the previous lecture, we learned that if the volume of a system remains constant during a process, then the work exchanged during the process is equal to 0. So the first law tells us that the change in energy of the substance is equal to the heat exchange between system and surroundings during heating or cooling of that substance. Earlier, we defined the constant volume heat capacity, C sub V, as the ratio of the heat, Q sub V, to the temperature change, delta T. As a result of the first law, we can now write the constant volume heat capacity as delta U divided by delta T, or du divided by dt. Du dt is the derivative of u with respect to t, a measure of the slope in a plot of u versus t. Sometimes you may also see the constant volume heat capacity expressed in a slightly different form as del u divided by del t, with a subscript v to indicate that the variable v is kept constant during the process, here a change of temperature. Note that the symbol del is used for quantities that are function of multiple variables. This ratio corresponds to what we call a partial derivative. If we asked ourselves what kind of experiments or real-life processes involve heating or cooling a substance at constant volume, we would have a difficult time identifying anything specific. The reason is that when you heat any substance, the substance tends to expand. Conversely, when you cool down any substance, they tend to contract. So doing an actual experiment where you change T by heating or cooling and keep the volume constant is not practical or feasible. However, such experiments can be carried out on computers, for instance, when we try to simulate the behavior of molecules. Another application of this concept is with theoretical treatments. For example, we briefly talked about the kinetic theory of gases. One of the results of this theory is that the energy of an ideal gas, U, is equal to the energy of the gas at 0 Kelvin, U sub 0, plus 3/2 times the universal gas constant R times the absolute temperature T. If we calculate the derivative of U with respect to T, we obtain C sub V equals 3/2 times N times R. And the molar heat capacity, C sub V sub M, equal to 3/2 times R. This result is actually very important, as noble gases, such as helium, neon, argon, and so on, have molar heat capacity values that are very close to the prediction from the kinetic theory of gases. In summary, isochoric heating or cooling processes are often of limited application, and we will see in a few slides that when we heat or cool down a substance, we generally keep the pressure constant. So we will need to talk about the constant pressure heat capacity.